Okay, let's talk a little bit about scientific notation and how we wind up using it in physics. So, first example I want to toss out here. Let's look at Newtonian gravitation. So this is the force of gravity, not when you're near the surface of the Earth, but when you are just any old thing interacting with any other old thing. This is what Newton said, that we get this constant g, which he kind of figured out. Then it's proportional to the products of the masses divided by the square of the distance separating them. And it turns out I cannot spell and say different words at the same time. So, why do we want to look at this? Well, we said that near the Earth, Fg is equal to mg. So that should mean then that g should be with the thing that our mass is multiplied by, should look like this: the mass of the Earth divided by the radius of the Earth squared, right? Now, you may have noticed over here I've conveniently located many of these variables. So let's see what we get. We have Newton's constant g, which is 6.67 times 10 to the negative 11. So this is why scientific notation is going to come into play. This is a very small thing. It turns out gravity, a very weak force. We only notice our weight because of how freakishly huge the Earth is compared to us. So that's g. The mass of the Earth is, this nice little 5.97 times 10 to the 24th kilograms. So if you ever feel that you are not, if you're ever feeling a little big, keep in mind that the Earth is several orders of magnitude bigger than you. I don't know if that helps or not. Not doing units, just numbers. And then divided by, we're going to take the mean radius. So kilometers, we need to turn into meters. Kilometer, remember, 1,000 meters, so that kilometer is 10 to the third. So this is 6,371 times 10 to the third meters squared. Alright. Let's see what we can do to clean this up a little bit. So first thing we got to remember, when we're dealing with scientific notation, we want to worry about the coefficients and we want to worry about the powers of 10. So let's try to start separating these. We got 6.67, that's our coefficient over here. We get this 5.97 coefficient over here. We can split these up because, again, multiplication doesn't matter what order we do it in, it all happens at the same time. And then we have this 10 to the negative 11 and this 10 to the 24th. The powers of 10 that we're going to separate out. Now this is a little confusing. These are nicely done in scientific notation. It's something dot something something times 10 to the whatever. That's good form. This, bit of a mess. So let's see here. This 6,371. That should be 6.37 times 10 to the third. So I got to go 1, 2, 3 from 6.37 back to 6,371 times 10 to the third again. Now, this is where we need to start remembering stuff. If we have, if we're multiplying things with like bases, we add the powers. So this is going to be the same as, hopefully you've done it in your head by now, because adding 3 plus 3 is something you should be able to do, 10 to the 6th. But then we got to square it. Just making things complicated. So, this is where things are going to get fuzzy. I'm going to say that 6.67, 5.97, and these two factors of 6.63, because we'll write this out. 6.37 because we're squaring that, 10 to the 6th because we're squaring that. All of these things I'm going to say are just about 6. So that's going to be a big old-fashioned 1. And then here, we're going to multiply these, so that's 10 to the 13th up top. Multiplying means that we add the powers. Multiplying on the bottom, 10 to the 12th. So, when we have going from here to here to here to our grand finale, in case you got confused, because it's getting a little messy. 1, whatever, we don't care about that. When we take the quotient of these things, we're going to divide them. So it means that g is 10 meters per second squared. Approximately, This is really an approximation because these are not all 6. So that's one nice example. The other nice example, let's take a look at the electron. So the electron has a mass, which is incredibly small compared to the Earth, has a charge, which is very small. We have this crazy constant. So what I want to know is how does what is the ratio of the electric force between two electrons to the gravitational force between two electrons? So the electric force is going to be Coulomb's law. So we get K. The electron charge, which we know we don't write like that, we write it like E. It's going to be squared. We're going to separate them by some distance. And then gravitational, we just said, looks like the mass, and it's the mass of the electron, not the mass of the Earth this time. You'll notice these look really similar. Turns out that's kind of important for physics. So we're going to wind up with K over G, that's a G, times E squared, the charge of the electron over the mass of the electron squared. So K looks like 9, yeah, I'll call it 9, times 10 to the 9th. G, we said, is 6.67 times 10 to the negative 11th. So already, we're going to see something interesting happen. E, we have up here as negative 1.6, but since we're squaring it, doesn't really matter too much, times 10 to the negative 19th. And then the mass of the electron we have as 9.1, not a negative, just a dash, times 10 to the negative 31st, squared. So, let's group out all the coefficients, and then all the powers of 10. So we have a 9, we have a 1.6, we have a 1.6, we have a 6.67, we have a 9.1, we have a 9.1. So, well, that's going to be messy. Powers of 10, we have 10 to the 9th, 10 to the negative 19th, 10 to the negative 19th, again because we're squaring stuff, 10 to the negative 11th, 10 to the negative 31st, 10 to the negative 31st. So, let's take a look at this. We got a 9, get rid of some 9s. Call these, maybe they're about 2. And call this, I don't know, so now we've got maybe 4 over, let's say, 60. A little less than 7. You know, this is maybe like 6 times 10-ish. Again, we're going for approximations here. This is the stuff we're interested in on the other side. So 9 and negative 19 is negative 10, so that's negative 29 on the top. And then down here we have, 62, 73. That seems pretty terrifying. So 4 over 60, that's another power of 10 down there, so that's 4 over 6. 10 to the negative 29th times 10 to the negative 73. So that looks like 2/3. Ooh, 1 minus 73 is negative 72, and then 72 minus 29 is a number. And that number I'm thinking of is, what do we got here? 3 brings us to 32, so 43. So, electric force to gravitational force. Electricity wins by a huge margin. It's one of those interesting quirks. So hopefully this is kind of a good reminder of how to deal with scientific notation. Again, you know, the short version is that you have a number that is like, 1.23 times 10 to the 34. And this is the general form of anything in scientific notation. And your calculator is going to look at it and it's going to tell you something like this, where E, that big capital E, is just times 10 to the. Alright,